Have you ever thought about why this sounds different than this? They're both an A, and yet you can tell that this is the sound of a piano, and this is the sound of a guitar. But what is it about the sound that makes your brain able to interpret the difference? If you were to ask a musician, they would probably say, oh, well, that's timbre. It's sort of like the texture of the sound. And you can look up this word timbre and you'll get a definition that says something like, it's the quality of the sound that is distinct from its pitch or its intensity. But this doesn't really tell you what that quantity is physically. Sound is a compression wave, meaning that it's the repeated compression of atoms and molecules in a material or a fluid, such as air. When these areas of compression strike an object, like your eardrum, they cause it to vibrate, which is how you're hearing me speak right now. But really, I'm talking into a microphone, and my voice is vibrating a membrane inside the microphone, which is converting the compression waves into an electrical signal. They'll look something like this, where the green line here represents the oscillating voltage produced by the microphone. We can use this signal to dig a little bit deeper and answer some very important questions.
Is mayonnaise an instrument?
We'll come back to that question. What you're looking at below me is a virtual oscilloscope. It's a way of visualizing the sound. It's taking the output of the microphone and plotting it on a graph for you to see. Now, as I talk, you can see that it looks like a jumbled mess because there's a lot of different frequencies at different intensities as I'm talking. But I can also play a nice clean sine wave, something like an A, which is what I played on the piano and the guitar earlier, which is a sound wave that has a frequency of 440 Hertz and sounds something like this. Now you can see this sound wave looks much cleaner because it's a pure frequency, just 440 Hertz, and comes out as a sine wave on the oscilloscope. Okay, I may have lied to you.
We've been duped! Duped! Bamboozled!
Hang on, just let me explain. That was a 440 Hertz sound wave, and that is an A. And I did play an A on the piano and the guitar. However, it was not that A. It was this A. The note I played on the piano and the guitar is actually 2 octaves below the 440 Hertz A that I played on the computer, where an octave is an interval between 2 sound waves, in which the difference in the wavelength between those 2 sound waves is a factor of 2. In other words, a note that is 1 octave below another note will have twice the wavelength, and a note that is 2 octaves below another note will have 4 times the wavelength. However, keep in mind that we describe the pitch of a note by its frequency, and the frequency is inversely proportional to the wavelength of the sound, because the speed of sound is roughly constant for different wavelengths. Put simply, this means that twice the wavelength corresponds to half the frequency. Here's what the first 4 audible octaves of A sound like. Now let's compare some of those notes to the notes on a piano and a guitar. Now, if you listened carefully, you may have noticed that you can actually hear each of those octaves in each of the notes on the piano and the guitar. And if I play those 4 octaves together, we begin to hear something that sounds kind of like a real instrument. Given this observation, you might think that The note A that I played on the guitar and the piano is actually composed of multiple octaves of A. And you would be right, but only partially.
I'm confused. I'm confused right now.
Hang on, I've got a button for this.
Panic. Nobody knows what they're doing. We're all eventually gonna die.
Sorry about that, I had the wrong button.
Just relax. Everything is going to be okay.
There we go, that's better. To understand exactly what frequencies are in a note from an instrument, I'm going to need to explain a different way of visualizing the sound so that I can illustrate it for you. To the left of me is the same virtual oscilloscope that we were using before, which plots the output of the microphone with respect to time. But we can do what's called a Fourier transform, which converts this graph from a function of time into a function of frequency, which is what is given in the plot below me, and also called the audio spectrum. Now as I talk, you can see just like before, it all kind of looks like a jumbled mess. But if I play a nice clean sine wave, like the 440 Hz A that I've been using, you can start to understand what this audio spectrum is showing you. As you can see, the waveform above looks just like it did before, a nice clean sine wave. But the audio spectrum below, there's a sharp peak centered at 440 Hz. This is because there is only a sound wave that is composed of one frequency, 440 Hz. This is the nice thing about an audio spectrum, is you can see exactly what frequencies are actually in the waveform that you see on the oscilloscope. For example, I can play two frequencies on top of one another, 440 Hz and 110 Hz. Now you can see that although the waveform doesn't look like it changed that much, it's hard to tell exactly what's in there in terms of frequency. In the audio spectrum, we can see very clearly that there are two frequencies that are making up this waveform, 440 Hz and 110 Hz. Now that we understand what the audio spectrum is, let's look at the audio spectrum of the guitar. And to get a better look, let's take a snapshot. Now let's look at the audio spectrum of the piano. Now I know it's not really a piano, it's a keyboard, but it does a fairly good job of simulating what an actual piano would sound like. So here's the audio spectrum of the piano. And again, let's take a snapshot so we can get a better look. Now we can see why the piano and the guitar sound different. They have different audio spectrums, but why are they different? And why do they look the way they do to begin with? Well, to understand that, we're going to have to talk about vibrational modes. Both the guitar and the piano produce sound by vibrating a string. In the case of the guitar, the string is plucked. And in the case of a piano, the string is struck by a hammer. But in both cases, the string is clamped at both ends. In the case of a guitar, those clamping points are the bridge and the nut. The string cannot move at these two locations. So let's take a look at what kind of vibrational modes we can get from a string that is clamped at both ends. What you're looking at right now is the simplest vibrational mode, also called the fundamental mode. It's called the fundamental mode because it is the longest wavelength that can exist between the two clamping points. You'll notice that the only places where the string is stationary is at those clamping points. However, we can have higher order modes, such as this one, where you can see at the center of the string is actually stationary. This is called a node. So the second order mode, shown here, has one node. And we can also look at the third order mode, which has two nodes. And this trend continues for all of the higher order modes, as shown here. Notice that each higher order mode decreases in both wavelength and amplitude. For example, the second order mode has half the wavelength of the fundamental mode, and the third order mode has a third of the wavelength of the fundamental mode. And that trend continues for all of the higher order modes as shown here. Also notice that each higher order mode has a higher frequency. This is because just like sound waves in air, the wavelength is inversely proportional to the frequency. Therefore, the second order mode has twice the frequency of the fundamental mode. The third order mode has 3 times the frequency of the fundamental mode, and so on. This is why I said it's only partially correct to say that the note on an instrument is composed of octaves. The octaves are in there, but an octave is separated by a factor of 2 in terms of its wavelength and frequency. That means that, for example, in these first 6 orders of the modes on a string, only the second and fourth order mode are actually octaves. The other modes are different intervals. However, now we know why the audio spectrum of the guitar and the piano are composed of separate but evenly spaced frequencies. These are frequencies that are related to the higher order vibrational modes of the string. And this collection of modes is known as the harmonic series. Now, if we look back at the audio spectrum of the guitar, we can see those first 6 vibrational modes displayed here. However, you may also notice that some vibrational modes appear to be missing, and not all of the vibrational modes have the same intensity. So why is this? Well, one reason for this is resonance. Some of the frequencies from the vibrating string can get absorbed by the instrument itself. For example, the acoustic guitar that I'm holding here has a resonant frequency that you can hear if I just tap on it. So if some of the frequencies match the natural resonance of the body of the instrument, those frequencies will get absorbed while other frequencies don't. But another important factor is the initial conditions of the string. In other words, how you cause the string to vibrate. Depending on what the initial condition is, some of the vibrational modes will get excited more than others. Here's 2 examples of how to cause a string to vibrate. The top of the screen shows a string being struck, similar to what would happen in a piano. The bottom of the screen shows a string being plucked, similar to how you would cause a string to vibrate on a guitar. The motion of the string in both cases looks similar, but it's not exactly the same. And we can break down the motion of this string into its vibrational modes of the harmonic series. For a plucked string, that looks something like this, where the black line represents the actual motion of the string, and the different colored lines represent the vibrational modes that make up the overall motion of the string. I want to take a moment real quick to give a big thanks to Dr. Dan Russell. I used a few of his animations from his website in this video with his permission. And his website is a great resource for anybody wanting to learn more about the physics of sound or music. He also has a YouTube channel that has some really good content as well. So if you're interested in learning those things, please go check out his website and his YouTube channel. The links to that are in the description, as well as links to other clips that are used in this video. Okay, back to the video. In this video, I've been referring to instruments that use vibrating strings, but everything that I've mentioned actually applies to every instrument. This is because any instrument relies on some vibrating object to produce the sound. For example, a woodwind instrument uses a reed, which acts sort of like a vibrating cantilever. And a brass instrument relies on what's called your embouchure, which is just a fancy word of saying buzzing your lips in a mouthpiece. In summary, the reason why instruments sound different is a combination of things. One, it depends on the type of object that is vibrating to produce the sound. It could be a string, or a reed, or your lips in a mouthpiece. Furthermore, it also depends on how you cause that object to vibrate. For example, with a string, you could either pluck it or hit it. And thirdly, it also depends on the body of the instrument, how it's shaped, and what materials it's made of. This is because if there are any resonances in the body of the instrument that overlap with any of the vibrational modes, then those vibrational modes will get absorbed and affect the audio spectrum. Okay, now that you know a little bit about the physics of music and sound, I have a couple of questions for you to see how well you followed along. The first one relates to the guitar. I'm going to play 3 notes on the guitar, but the first time I play them, I am going to press the string down onto the fretboard. The second time, I'm simply going to place my finger on the string without actually pressing it onto the fretboard. Okay, so here's the first 3 notes by pressing the string onto the fretboard. Okay, now I'm going to play those same 3 notes, but without pressing the string onto the fretboard. Now you may have noticed that when I was pressing the string onto the fretboard, I had to move my hand up the neck of the guitar. But when I was simply placing my finger on the string without pressing it onto the fretboard, I had to move my hand the opposite direction, down the neck of the guitar. So the question is, why? Why, when I press the string onto the fretboard, I have to move my hand up the neck of the guitar, but when I simply place my finger on the string without pressing it onto the fretboard, I have to move it the other direction? Now, the second question relates to your voice, because you don't actually need an instrument to make music. You can just sing. So I can sing an A, ah, but I can sing it in different ways. O, E, ah. So then, why do those sound different? They're both being produced by my vocal cords, but what exactly is it that makes the vowels sound differently? And furthermore, can you sing in consonants? Like f, s. Do those count as notes? If you think you know the answer to these questions, go ahead and put them in the comments section below. And in the future, I'll make a couple of short follow-up videos explaining the physics behind these 2 questions. So if you don't want to miss that, make sure you subscribe and ring the bell so you get notifications for those videos. Do it. Oh, wait. I'm sorry. Does somebody have a question? Yeah, you. The one not wearing a shirt.
Is mayonnaise an instrument?
No, Patrick, mayonnaise is not an instrument. Horseradish is not an instrument either.
Well, there you have it. I guess mayonnaise is not an instrument because it doesn't produce a harmonic series.
When you came to me 15 years ago, you told me that everything was a drum.
Whoa, whoa, whoa. First of all, I don't know you. And 15 years was a long time ago.
Everything is a drum.
I mean, I guess anything can be a drum. I mean, drums also have vibrational modes, but they're damped so quickly that gives them their percussive.
I left my wife.
And who are you? I don't know what to tell you guys. What do you want me to do?
You were just playing it wrong.
You guys you're really gonna make me do this, aren't you? You're really gonna make me do this? All right, let's do this.
Did you know?
Mayonnaise.
Is a drum? Every Everything